Hello, everyone. Today we're going to solve the Leet code question. Find the index of the first occurrence in a string. So essentially, we're going to have a word we're going to search through, and we're going to be given a key. And what we want to do is we want to search for that key within our given word. If we do locate the key within our word, then return where we started that key, that index, where we found the first letter of our key. If not, then we're going to go ahead and return -1 because we never found the key within our word. However, notice the terminology they're going to use is instead of key, they're going to use the term needle. And then instead of kind of search word or word, they're going to use the term haystack. So we're searching for a key within a word, or we're searching for a needle within a haystack. And this goes on to explain that same logic, which is we're going to go ahead and return the first occurrence of the needle within our haystack, or -1 if the needle is not part of our haystack. If we looked at two test cases, we could see that in this case, our word is sad but sad, and our key is sad. We could see that this key pops up twice here, starting at index 0, and then here starting at index 6. However, we're looking for the first occurrence, so we would return index 0. And then in this instance right here, we could see that our word is Leet code, and we could see that our key is Lido. Lido, this key never is found within our word. And for that reason, we're going to go ahead and return -1. That's really the crux of it. Another way of kind of looking at it is like this right here. This is just a separate test case. So if I'm looking for the key cool, and within the word cool, what I would do is I would see that this is not the word, this is not the word, and so forth until I get to here, and I would go ahead and return the index from this location. I'm not going to count it, but this is just the index that I would return. So that being said, for this problem, we're going to cover two solutions that I went over, or that I created. The first solution is going to use a nested for loop, and the second solution is going to use a single for loop. But it's a little bit more verbose, and it also has the same time complexity as the first solution. So both of these solutions have the same time complexity. They're going to have a time complexity O of n times m, where we define n to be the the size of our word, and we define m to be the size of our needle. They essentially boil down to both being nested for loops, with the outer loop being the haystack size, and the inner loop being the needle size, really. So that's why it's going to be the haystack size times the needle size. You can imagine as part of our logic, like let's say, for example, actually, before I continue, let's go through some of this logic to see why that would be the case. So what we're going to do is we're going to go through each haystack element, and we're going to use that as a starting point. And then from that starting point, we're going to check if that element and the rest of it matches the needle. If it does, then we're going to return the haystack element index, the starting point index. If not, we're going to go to the next haystack element. So we're going to change our starting point and increment that forward by 1. So you can imagine if our haystack size is 10 and our needle size is 3. So maybe I should probably list this as size. If our haystack size is 10 and our needle size is 3, you can imagine that these are just placeholders. What would happen is, for this starting point, what we would do is I would want to search the 3 elements from it. So the current element plus the next 2 elements after it, to see if it matches my key or matches my needle. If it does, then I'll go ahead and just return the current starting point that I was on. If not, then I'll go ahead and change over my starting point to this position, or this index. Or yeah, technically it's a position since I haven't offset it by 1. So I would go to this position. And then I would go ahead and do 3 comparisons here according to the needle size. Is it the same needle? If it is, then once again, we'll go ahead and return that index. If not, we'll go to the next element. And we'll keep moving forward. So notice for each element, a haystack element, I'm doing 3 comparisons because, or up to 3 comparisons, I should say, because that's the size of my needle that I'm searching for. There are a few ways that we can optimize this. We can go ahead and say, as soon as we find a disparity, as soon as we find kind of where there's a dissimilarity, then we can cut it short. So we're not going to get this worst condition like n times m. That would be very rare. But since this is big O of or this is time complexity, this is big O, we're looking for the worst case. So that's how we derive this equation. There is also something else to consider is that notice there are going to be boundary conditions, because the last place where I could potentially find the key is at this position, just because I only have a total of 3 elements starting from this position left. So if I were to move to this position, notice I can have 2 letters. I'll have 2 elements involved, but there's no other letter except kind of out of bounds data, and that would lead to undefined behavior. So we want to make sure that we don't. We want to stay within our boundary conditions. So that's just something to consider. So boundary conditions are important to consider, right? And we'll mention that in just a bit. So that's really it. Those are going to be the 2 solutions we're going to cover. We're going to use nested for loops first, just because it's a bit simpler, and then we're going to go a different method about it, but it's going to have the same exact time complexity. I do also want to preface this by saying that we're not going to be using the KMP or the Knuth-Morris-Pratt pattern searching algorithm. That one would have a linear time complexity, and it would use some additional space. So it would to go ahead and streamline the time complexity. However, this solution, I've only taken kind of a cursory look at it, and I don't really kind of fully understand it yet. So that's one challenge, and then the other part of it is it looks a bit complex. Like if we were to look at this solution, we could see that it's can get a bit tough. So I do apologize. I'm not going to be covering it today, perhaps for a later video, but that's just something that to consider. So once again, we're just going to be going over the brute force solution in this example. So going back to that, let's get started. So what are we going to go ahead and do? We're going to go ahead and actually, should we take a look at a test case according to this? Yeah, let's go through some example logic to make sure you fully understand it. So let's consider our key is cool. All right, if our key is cool, and then this is our word, or this is our haystack. So cool. So what we're going to do is we're going to have our starting point. We're going to have our starting point right here at this first element. And what we're going to do is we're going to check it to see if it matches the key. So we're going to check it 1 letter at a time. This matches the key so far. It does match the key so far. It does match the key, but then the K ruins it. The K ruins it. So at this point, we can go to the next element. So we're going to move our starting point over to the next letter. So this O, does it match the key? Nope. O does not match C. So then we're going to move our starting point forward. Does this O match the key? Nope. So at that point, we're going to move our key forward. Does the K match our key? Nope. So we're going to just move our key forward. Does the C match the key? Yes. The C matches the C. The O matches the O. The O matches the O. But then the K does not match the L. So at this point, we found a discrepancy. So we're going to move our starting point over again. We're going to move our starting point to this O. And the O doesn't match, so we'll move our starting point. The O doesn't match, we'll move our starting point. The K doesn't match, so we'll move our starting point. The C does match. So what we're going to do is we're going to continue to the next letter. The O matches the O matches the O, and the L matches the L. Now notice in this case, there's 4 matches at this point, and that's the same size as my key. So whenever the number of matches that I have matches the key size, I know I found the whole word. So at that point, I know that this is the first occurrence of it. So how do I return the index from where it started? Well, we just return the starting point index, right? So if whatever the starting point index is, we would go ahead and return that. And that's really the whole algorithm. So please feel free to review this section of the video if you are kind of a little bit unclear. Make sure you feel comfortable with this test case, because that's going to be, I purposely created this test case so that we can show kind of like fakes. When fakes happen, what we do is when we have partial matches, I should say, whenever we have partial matches, so we're matching along, everything's going well, we continue to match kind of like in the COO. But then we have what's called a partial match because we find a disparity, then what we're going to do is we're going to have to bring it back. We're going to have to bring it back to here. And so for this for loop, it's really easy to do, or for the nested for loop, it's easy to do so. If we're only use one for loop, it's a little slightly bit trickier, but it's going to be the same logic. So whenever there's partial matches, just go back. Anyways, I hope that made sense. And then I also hope that it made sense that, when we find the same number of matches of letters as the size of our key, then essentially we found our key. So that should also be an important thing to consider. So what we're going to do is we're going to start off by creating a variable called letters matched. And we're going to next iterate through our haystack to use as a starting point. So let's go ahead and iterate through our haystack. So int I equals 0, I is less than, or the index is going to be haystack.size, I plus plus. So these are going to be our starting points, our potential starting points. And what we want to do is whenever we have a new starting point, we know that there have been 0 matches. We haven't found any matches. So when we have a new starting point, our letters matched is reset, essentially. So initially you can consider it as it's first initialized to 0, but it's really reset for each new starting point that we encounter. The next thing is we now want to iterate through all of our key. So for each elements for each haystack starting point, we want to go through our entire key. So let's go through the key. So for each I, or I should say j, let's go ahead and create a different variable. J is 0, j is less than my key size j plus plus. And this is all it's saying is that we're going to iterate through the entire needle for each haystack element. Right? And this is not necessarily true in the sense that we can go ahead and optimize this. We can stop short of this whenever we find disparities, but potentially we would iterate through the entire needle for each haystack element. Right. So for each haystack element, we'll go ahead and go through the key. Now that we have our nested for loop set up, what we want to do is we want to see if we find a match. Do we find a match? Let's check for a match or a match. Now, in order to find a match, we would go ahead and say if haystack at the index I, so at the current starting point, plus j, right? So plus j. If it's very important that you include this so that we can continue iterating through not just the starting point, but the rest of the characters. Because if you just went ahead and just used I, you would keep using the same starting point, and that's not true. Unless you'd get like a false what's called a logic error. Unless of course you like the only cases where you would get true is like if your key is all the same letter and you're continually matching to the first letter of the starting point of your haystack. So just know that would be the wrong logic. So we want to go ahead and set it up like this. So if our haystack at the index I plus j is equal to our key at the index letters matched. And so notice we're using letters matched, not only to keep track of how many letters we have matched, but we're also using it as an index, just because initially this is 0, so it's searching for the first letter within our key. So another way of saying it is that this would correspond to the first time it would correspond to the letter C, right, for cool. And then if we were to find a match and we increment this count, then it would refer to the index 1, which is the letter O. And so you can see how this, it not only works as like a counter, but it also works as a way to keep track of the correct index. So if this does match, so if we do have a match, before I continue, I do want to state that this could potentially lead to undefined behavior if we don't check it. The reason is that I'm using this as a starting point, and this is going through the entire size of my haystack. These are going through all the indices within my haystack, so these are valid. Are these valid? Not always. because I is always going to be valid. Adding j to it, adding an offset to it is not necessarily going to be valid, because what if I'm already at the last element and then I add j, which is, let's say it already looped through some values. This could potentially lead to some out of bounds array issues. So what we want to do is we want to validate it. We want to use some boundary conditions. So we want to check that I plus j is still within the bounds of our haystack size. So it's still with less than the size of our haystack. And we'll go ahead and place that in the front so we could short circuit this logic. So we could say if it's within our boundary conditions. So if this index is still within the bounds of our haystack size, or within the bounds of our haystack string, then we can go ahead and use it and access that element. So we also want to check the boundary conditions. Check boundaries first, boundary first, then check match. So hope that makes sense why we're doing it that way. So if we do find a match, we can go ahead and increment letters matched. So just, count the match. And then additionally, every time we find a match, we potentially found the word, right? So if we found a match, then maybe it's a single letter word. We could have found the word. If we find 2 letters and maybe it's a 2-letter word, we found the match. So every time we increment our letters match count, that could potentially result in that being the last letter to complete our word. So we want to make sure that we check that. So if the letters matched is the size of our key, so we found the word. If we found the word, then we know that we can just go ahead and return the starting point. Well, what was the starting point? This is the starting point, I, right? The counter that we're using in this instance. So we would go ahead and return I, which is the starting point. So return the starting point of the word. Okay, so that's really how we take care of instances where we find a match and if we actually complete the word. But what if we don't find a match? Well, if we don't find a match, so do not find a match, and then what we want to do is we want to iterate to the next starting point in our haystack element, right? So we want to go ahead and go to the next element within our haystack because we want to go to the next starting point. So what we're going to do is we're just going to break out of this loop. And this is what I mean by we're not always going to have the instance where our time, we're performing n times m, or the size of our haystack times the size of our needle, because we're going to have a lot of cases where we break out early. And so that's why it's really going to be so if there's distinct letters and we're not really finding a lot of partial matches, then it's closer to linear time complexity, to be honest. But when there are a lot of partial matches, that's where we kind of get in trouble with this algorithm. But anyways, that's really the logic. So if you find a match, you go ahead and increment that. If you find a match, I should say, and it's within bounds, you go ahead and increment that count. And then every time you do find a match, you want to check if you completed the word. If you do, go ahead and return the starting point. If you don't find a match, go ahead and break out of the loop so that you can go to the next starting point, next starting point, next starting point, and so forth. And that's really it. Now, if you complete this nested for loop, or sorry, if you complete this logic here with the nested for loop, and you haven't found the word, then there was no occurrence of that key within the word. So for that reason, if we reach the end of this nested for loop, we're going to go ahead and return -1, which means we found no occurrence of the word. Okay, so that's really our solution. That's all there is to it. So we'll go ahead and run it. And hope I didn't make any syntax errors. Okay, that looks good. That's really the solution. I'm going to go ahead and now switch on over to another solution that I kind of created. This one does the exact same thing. It has the sign, once again, it has the same time complexity. For that one, I'm not going to code it live, but I'm just going to go ahead and go through, paste the solution, and then talk about what it does. Like talk about the logic or the pseudocode, and then go through the actual solution so that we can kind of see what's happening. Feel free to stick around for this one. If not, I completely understand. There's no hard feelings, just because this next one is a little bit lengthier and you don't get the live coding example. So I'm going to go ahead and erase this and enter this example right here. So let's go ahead and place it here. And for this, let me comment it out, or let me uncomment it, I should say. So for this one, what we're going to do is, you'll notice, actually, the first thing I want to say is you'll notice that the logic only uses one for loop. So you might say, how is this going to be a nested for loop essentially, or how does it equate to a nested for loop? And that's really because the counter that we're using, I, to iterate through our haystack, we're going to manipulate it whenever we have partial matches. So this is the case when we have partial matches. And I say partial matches because we had some matches, but then eventually there was a disparity. And for that reason, you know, things didn't work out. And what you're going to do is you're going to manipulate the I, which is the counter that we're using to traverse through our haystack. So by manipulating the I and going backwards, that's how we essentially get from this implementation to the nested for loop. They're going to be pretty much the same. And we're going to see it in just a moment. But just know, because of this condition, it's no different than the earlier solution that we saw. It's just another way of coding it, but it's the same time complexity. Everything's pretty much the same. So how are we going to tackle this solution? Well, number one, we want to iterate through the haystack. Okay, pretty straightforward. Number two, if we haven't found a potential starting location, and we find one right now. So what is a potential starting location? That's when the key, the first letter of our key, matches the current letter or the starting point of our haystack. So the current element of our haystack matches the first letter of our key. So that's what we define as a potential starting location. So if we haven't found one yet, or technically we may have discredited one before, then what we're going to do, and we find one currently. So if I find a first matching letter, I'm going to set a flag to denote that as a potential starting location, and we're going to store the index of it. So we're going to store that index to be able to refer to it later so we can return it if it ends up matching the whole word. So let me repeat that once more. So we haven't found a potential starting location, but we find one right now. So we find the same matching first letters. Then we're going to go ahead and set a flag and store the index. So now the next thing to consider is if we do find a match, what we want to do is increment the match count. If we do find a match, we just want to increment the match count. And then whenever we increment the match count, we want to check if we found the whole word. If you found the whole word, return the starting location. How do we have that starting location? Well, it's from this location, right? So so this potential starting location, that's what we would return in this instance. Now, what if we didn't find a match, but we never found a potential starting point? So if we didn't find a match, okay, that's one thing, but we never potentially started. So we never even got the first letter. So I don't have to go back in time. I don't have to consider that as going back in time. I don't have to go to a previous start point. I can just go to the next iteration. I can go to the next starting point. There's really no problem there. But the issue becomes when we have partial matches. So this is the partial match case. If we didn't find a match, but we had a potential starting point. So if we did have some previous matches, but now we no longer have a match, then what we want to do is we want to return back to the potential starting location and discredit it as a potential. So what that means is we're going to go to this case, go back in time, and we're going to discredit it by resetting our flag. So instead of it saying that this is a potential location, we'll set it to false. We'll reset it to false. And then we'll also have to reset the number of letters matched because we were keeping track of how many letters we had previously matched. We might have matched 3 letters, 4 letters, right? So we have incremented our count previously. So we're going to have to discredit it. So what that means is reset that back to 0. And then the last thing is, very similar to our previous case. If we reach the end of our haystack without finding the needle, you go ahead and return -1 as there are no occurrences. So this is kind of just like the very end of our loop. So if we finish our loop and we haven't found it, then go ahead and return -1. All right, so pretty straightforward. So let's go ahead and start off with our variables that we need. So the letters match to 0. We assume that we haven't started, we haven't found any matches. And once again, once the count of this matches the size of our needle, then we know that we match the entire key. And so at that point, we can return our answer, which is going to be the potential starting location. Here, this is going to be our flag, and this is going to denote whether we have a potential match. So did we find the first letter? Did the first letters match? If we did, then we go ahead and change that to true. If we haven't, so we'll just keep that as false. Or if we find a partial match, right, then we'll go ahead and reset this back to false. And then this is the potential match index. So whenever we convert potential match from false to true, that's when we're gonna go ahead and update the potential match index to our whatever current index we're on. So where did we find that first letter? And that's so that we can kind of easily return this variable instead of doing some logic where you might find some other Leet code solutions where they return, I think it was, the current index +1 minus the size or minus the number of letters match. So you could do that logic, which is completely fine, but I prefer to use kind of a variable for it just to kind of make it more descriptive, right? It'll make a bit more sense than when you're kind of looking back at your code, maybe like months later. And then we're for the sake of maintainability or simplicity, I should say, we're also going to say what's going to be the first letter within our key, first letter within our needle. Well, that's just going to be needle at the index 0, right? So that's just something so that whenever we code this out, it'll look simpler rather than saying needle at index 0. So now that we got that out of the way, let's go with the actual logic. So we're going to iterate through our haystack using the index I. Right, so I is going to be our index as we iterate through the haystack. Just want to keep that in mind because we are going to mess with it in this case. So if we haven't found a match, right? So if our flag is false and we find a match, we find that the current element of our haystack matches the first letter of our key, then what we're going to do is we're going to say, okay, so at this point now we found a potential match, and we're going to keep track of that index so that we could potentially return it if we end up finding the whole word. And now here we're going to set up a Boolean as well for match. This is just because I found myself using match several times and it just kind of looked ugly to reuse that. So I'd rather just keep it in a Boolean. So if the current letter within our haystack matches the current letter within our needle, or the current letter within our key. Once again, we're using letters matched as index, so that way we know which letter we care about for the key. So as we find more matches, then we increment that letters match. And since we're using it as an index, we continue going through the letters within our key. Anyways, that's a long way of saying, so if we do find a match, we're going to go ahead and stick it in this Boolean. So it's either going to be true or false. If we find a match, it's true. If we don't find a match, it's false. So if we find a matching letter, we're going to go ahead and, just like before, increment our match count. And every time we increment our match count, we want to check, did we find the whole word? If we did, return the potential match index, return the starting location. And that's why we kind of wanted to set up these flags, so it made it a lot easier. So look how cleaner this is to return the potential match index as opposed to, for example, something like, I think it was like, what was it? I think like I minus the letters matched +1, right? So you might see solutions like this. I just feel more comfortable returning this. Now that's very straightforward if we find just continual matches. So if we continually find matches, then that's where we are. This is a pretty happy case. If we don't find a match, and also but we haven't found a potential starting point, then that's okay. That's fine. We haven't found a first matching letter, so we can just go to the next haystack element. There's really nothing else to do. So you can imagine in this case, so the letter E. Actually, do I want to think of a test case at the spot? No, that's fine. So if we haven't found the first letter, then we're not going to have to go back in time. So we haven't found any partial matches, so we don't really have to go and do anything funny with manipulating our I, manipulating our counter. But if we find a potential match, so if we don't find a match, but we have started before, so we know that our flag is a potential match. So we had already started this train. There were some matches, but now currently there is not a match anymore. Then we're going to discredit the potential match index. We're going to go ahead and say that was like a false positive. So how do we do that? We're going to go back in time to wherever we had found that potential match index. We're going to go ahead and reset our flag. We're going to go ahead and reset our numbers of letters matched, and that's really it. And we're going to continue to iterate through this until we reach the end of our haystack. If we don't end up finding any occurrences, or if we don't end up returning the potential match index, that means at no point was there any occurrence within our string. So we're going to go ahead and return -1, just to indicate that we never found the key within our word. So I do apologize for the lengthiness of that. I realize that this solution right here kind of can be a bit more verbose, but I hope that it made sense. If you have any questions about this solution, or whether it's the first solution or the second solution, please let me know. I'd be happy to maybe kind of share any information within the comments. Let me know what you thought of it. And if you had a preference, whether it was the first solution or the second solution. I kind of like this one, but the first one's also nice. I think I prefer, no, actually, I think I prefer the first solution just because I don't have to go back in time and mess with the counter. This is something that, kind of strikes me as a little bit off, that I have to go back in time this way rather than, using a nested for loop, which actually, now that I think about it, probably looks a little bit cleaner. But that being said, let me know what your preference is. And then also let me know in the comments if you're familiar with the KMP algorithm, if that's something that you've coded out, because it does look a little bit tough. So hopefully, if you have, share that with me, so I could say that that's pretty impressive. But thank you so much for watching. I really appreciate your time. If you haven't done so already, please like, share, and subscribe so that I can keep coding out these LeetCode solutions. And then also let me know some feedback if there's anything I can do to make improvements. The one thing I won't do, however, is make edits to the videos. And that's just because I want to save time. I want to make sure that while I am going through solutions online, I don't want to sacrifice any significant amount of time to edit videos, to make them look perfect, just because I'd rather spend that additional time learning and posting out some more solutions, or just kind of living, life, enjoying life. I previously used to edit videos, but it would take a lot of my time. So I'd rather prefer to just kind of code them live. Plus, I feel like this way you guys are able to hear me in the moment and see that, this is how I code it out. This is, how I tackle problems. And maybe that extemporaneous style makes you feel a little bit more comfortable. But enough about that. Thank you for watching, and I hope to see you soon.